What I'm going to be talking about is a project that I've been working on for the past couple months that's blending a lot of sort of different disciplines, digital fabrication, 3D modeling, Python, of course. And so this is my first time sort of talking at length about the project, so hope you guys find it a little bit interesting. Starting out just about me, I work as the developer experience guy at Tempo IQ. I have two of my colleagues, Patrick and Sam over there. And we are a Chicago-based startup that do sensor data analytics. I'm also a member of Pumping Station 1, which, if you don't know, is a hackerspace on the north side of Chicago. So it's a space that you can just pay a monthly membership fee, and you have 24-hour access to all these really cool tools and services they have: 3D printers, wood shop, metalworking, all this stuff, and CNC routers, and that's sort of what got me down this path to begin with. So I do a lot of side projects. Yes, and yeah, and Carl, who's behind the camera, was the one who invited me here. So thank you, Carl. So let's. I'm going to sort of start at the end. This is a coffee table that I built with the help of Python. So here's a couple other shots of it. So you can. So basically, it's half-inch Baltic birch plywood. There's no glue or fasteners or screws or anything like that. It's just pieces of wood that fit together with a custom cut glass top on top. And this was something that I did with the help of a tool at Pumping Station 1 called the ShopBot, which is a giant CNC router. So if you don't know what a CNC router is, it's basically a drill on an arm that you can program to move and cut out different shapes. And it does a lot of other stuff, but that's sort of the general idea. Here, I'm going to, I have a video sort of showing some of the parts of assembly. We'll actually watch it on YouTube then. So this is sort of time lapse, but you can see it's cutting out all these parts from a piece of plywood. And it's doing a couple passes because it can only cut a certain depth. And then here's me actually assembling the raw pieces for the first time after cutting them out. It speeds up because it's a little bit of a longer process. So there's a lot of other work beyond this. There was more on the woodworking side of tons and tons of sanding and finishing and making sure that it's not all sloppy and gives everyone splinters, but you can sort of get the idea of how it comes together like that. So that's hopefully gives you an idea of what thanks, of what I built. So then there's, again, the finished product. So how did I come up with this idea? I saw this tool, thought it was really cool. I saw people doing really interesting things with more like carving and etching designs, but I thought it would be interesting to do something that involved a little bit more construction, something that would be a lot harder to do without access to a computer-controlled tool like this. So something that you really need to have high precision parts that you wouldn't need to buy off the shelf. So there are tools to fabricate this stuff, but I wasn't really aware of how I would go about designing something like this. It was just sort of this concept that I had of this sort of assembly method, and I didn't really know if was this a well-traveled path? Is this something that I can just install a program and do this in 5 minutes, or is it something that I would be more trailblazing? And it wound up being somewhere in the middle. And also, I just wanted a new coffee table. I bought one on Craigslist for like $20, and it was not that cool. So that was another big driver. So what does the fabrication side look like? This is not the sort of the core of the talk, but it's really important to sort of just have a concept of what sort of how it works. So there's two main programs that most people at PS1 use when they're working the ShopBot. And it's sort of a pipeline process. So you start with like an intermediate format that's some sort of vector graphics file, like an Illustrator file or SVG or something like that. I guess to take a step back, vector graphics as opposed to raster graphics, which is usually what you would display is out of pixels. A vector graphics file uses vectors, which means that it's infinitely scalable, like an SVG file online is a scalable vector file. So basically the point of that is that it's defining the actual shapes of the strokes, not just the pixels that connect to form the shape. So that allows for easier machining because you can actually tell the machine follow this path. So we use a program called Vectric vcarve to convert these sort of common vector formats into a format called G-code. G-code is really ugly, as you can see on the right. It's super low-level machine instruction that runs on a whole bunch, that's supported by a whole bunch of different computer-controlled fabrication tools. It's like, I was reading the Wikipedia page preparing for this talk. It's like, it was developed like 50 years ago. So it's basically just a whole bunch of instructions about where to move the cutter. So not very user-friendly. So that's why a program like vcarve to sort of abstract that away. Then the ShopBot software is something that runs on the host machine that that is connected to the ShopBot itself. So that's sort of what's directly controlling the ARM and running through the G-code step by step. So that's sort of what the sort of the well-traveled path is. The question, of course, is how do you get those vector images to fit together like that? So that was sort of the challenge that I embarked upon. So taking one step back, this is an inspiration that I had for the actual design. This is a structure in Sevilla, Spain called Metropol Parasol. It's allegedly the largest wood structure in the world. It is awe-inspiring if you have a chance to see it in person. This picture, which I took, does not really do it justice. But you can sort of see it's a very organic, flowing kind of shape, but made out of flat wood parts, and it's like 35 or 40 feet tall. So these are like tents and buildings behind it. So it's a massive structure. So this stuck with me when I saw it and wanted to do something like that. You can't just build something like that as the first step in a project. You sort of have to iterate. So the first thing I did was sort of my hello world of this CNC assembly. So CNC, I've used that term a couple times, is computer numerical control. It generally is sort of an umbrella term for using computers to make stuff. So some people would consider 3D printing a CNC technique. So the ShopBot is what you saw it doing, where it's being controlled by a computer. So when I talk about CNC, that's what I'm referring to. So my first experiment with this kind of construction technique was sort of my hello world, was a ShopBot Saurus Rex. This is about a foot tall. I found a pattern online from this Instructable, which was actually an Instructable for a 6 foot tall version of it. I scaled it down a little bit because I just had a little scrap of wood. But it was sort of just playing around with the concept of pieces that fit into each other. And I didn't have to actually do any of the design work. So it was more just sort of figuring out how to handle the thicknesses of things and make sure that worked how I would hope it would. The next thing I did was actually sort of start from my own model and generate these slices. So I used Blender, which is a 3D modeling program. It's used a lot for like computer graphics. There's like some modeling for like game, characters in games a lot of times is done in Blender. It's used a lot for like computer animation, like Pixar type movies. It's free and open source, which is awesome. It's like, it's the best out of all the sort of semi-pro open source creative tools that I've seen, like GIMP and some of the other ones. That like Blender is least of what I've played around with is sort of the highest quality, very comparable with the commercial options. Then I used, so I made a model sort of the overall shape in Blender, and then I used a program called 123D Make to convert that into fabbable parts. So 123D Make was actually recommended to me by my coworker Patrick, who's here. It's an Autodesk application that does exactly this. It takes a 3D model and will let you build slices that fit together. And they have a couple other ways of building things, like sort of stacking slices on top of each other. So I was like, oh great, this already exists. That'll save a lot of time. So this is the model that I started with, sort of an initial concept in Blender. This is what 123D Make does. So on the left is sort of what their 3D rendering of it looks like, and then on the right is what it outputs as the vector image. So you can see each of these is a part, and those slots are how they fit in together. So you tell it the thickness, and it sort of works it all out. So that was actually pretty cool. It worked, and I built a physical model. So this is about 8 inches tall. And so that was a good success, sort of one step more control, sort of understanding the process a little bit better. But there were some problems with Make. It's free. It was designed to do exactly what I wanted to do. And there are a lot of cool built-in features that I didn't even explore, like different construction methods. I had a lot of problems with it though. Mainly it was unstable. I was getting a lot of crashes, especially with more complex models that had a lot of curvature and just more surfaces. It's just a GUI. There's no programmatic interface, and therefore it was sort of hard to extend. So there was there were things I wanted to do, for instance, like add cutouts into large empty spaces in the pieces so that it would look more like a skeleton or a wireframe and less like solid slabs like this. And that was something that, it outputs, a vector file, and I could manually edit it, but that isn't very fun. So I started to look for other solutions. So I wanted something, sort of a bizarre combination of requirements that is probably impossible to find. Something that has sort of that's not just a programming language, something that has a little bit more of a workflow for, exploratory design, but also has precise reproducible operations. So something that, once I get something that I like, I could generate a whole bunch of models and then pipe them through a pipeline and, sell these tables on Etsy or something. I don't know. And I need the output in this 2D vector format that could eventually be put into the shopbot. But I also wanted to have some awareness of like the 3D concepts, and how things intersect, so that it could do the slices correctly. So as you would probably imagine, it's not easy to find a tool that does all this stuff. The first place I looked was programmatic CAD tools. So there's CAD is computer-aided design. It's generally more about building like parts to machine. Like if you need a very specific bracket to attach, a chair back to the base or something like that, it's the tool that you would use to create the model to send to the manufacturer to create the molding, whatever. So there are tools that have programmatic interfaces. So this is a couple of the ones that I looked into. Some of them have Python APIs, which is cool, but they weren't really what I was looking for, just because they weren't really aware of the concepts that I needed them to be aware of, especially with outputting the formats that I needed and inputting a sort of an arbitrary 3D model. I kept coming back to Blender because I was using it for actually building the initial models. It's definitely more oriented toward artistic uses. It has an awesome Python API, which I'll get to. But has anyone here used the Blender Python API? Cool. It's really cool. It's a really big, well-supported project, so there's a lot of resources, not so much on the API side, but just for the software overall and sort of instructional videos on how to use it. And it's open source, which I would be willing to use something that wasn't open source, but I don't know if I would really be willing to pay a lot for it, and it's just a nice plus. Why not Blender? It isn't CAD, so it doesn't really have these concepts of in two parts intersecting. It'll just render whatever is visible to the camera. It's just not designed for doing this sort of physical construction. It's mesh-based, which I'll get to, but basically it's just a different fundamental concept of how you build objects that doesn't really lend itself well to making physical things. So yeah, basically it's just, the paradigm wasn't a great fit, but really what I needed was just some 3D environment that had an API that I could program in and see if I could do what I wanted. So I'm sort of show you a couple of the key concepts of Blender, because it's really cool, and then that'll sort of segue into what it has, what it doesn't have, and what I built to supplement its capabilities. Back. Come on. Stand by. Oh, come on. And, all right, let me see if I can shock it into obeying me. Interesting. All right, I think I got it. All right, quick tour of Blender. And that's back up there, great. So this is what you see when you first open up Blender. This is an example project. There's a lot of stuff going on around the side of the screens. Don't pay too much attention to that. The important thing is the stuff in the middle. So you have this nice 3D universe. And just to sort of drive home the point that this is not sort of a 3D design program, it's more of an animation and rendering program. In the default scene, there's a camera and a light because they expect you to ultimately render this into a pretty picture or movie. But there is this cube, which is what we're actually interested in, because in addition to this nice solid surface, it also has another way of interacting with it. So we can move the cube in 3D space, but we can also shift into what's called mesh mode or edit mode. And that will give us access to the underlying data that builds this cube into a 3D shape. So the fundamental parts of a mesh are a vertex. So this, you can see the point is called a vertex. So I can select different vertices. And an edge is a connection between two vertices. So now I have this edge selected. That one's kind of hard to see. I'll do this one. And then you can also select a face. So if I select all 4 of the vertices that bound this side of the cube, that actual side lights up. So that's showing that we've selected not only those vertices and the edges, but the face as well. So you can edit any stuff that you select. So if I just select this one vector, I can move it. So I can just sort of drag it in any one axis or freeform. And then that once I release, that's it's actually deformed. I can do that for an edge or for a face. So I'm going to just take this face and drag it up and drag it over here. So that's just sort of basic manipulation of the mesh itself. But we still haven't really done too much. It's sort of hard to see how to get from here to a table or some more complex shape. There's a lot of tools in Blender, and I spent a lot of time just sort of figuring out how they all fit together. There's a lot of really good instructional videos. Just to sort of give you an idea, there's one tool called the loop cut, which will so like a loop cut will allow you to add edges and vertices to an existing object. So you can see it's highlighting sort of different loops through this object. If I select this one, now I can actually slide this loop to different points. Let's put it there. And now it's actually been added to my mesh. So now I have these extra points that I can play with. I can drag around. And then if let's see, I'm actually not sure why it might went into clear mode, but I'm not going to worry about that. And then when I come out of it, now we're back in object mode, and I can still move this around as a complete object. So you can sort of see how you can build up with a lot of these different tools to actually make something real. There's a whole lot of other stuff that Blender does that I'm not going to get into, but hopefully this gives you a little bit of an idea of how you can can create and manipulate meshes and what the parts of a mesh are, because they're going to be important later on. So one other thing that's really cool about the Blender UI is I mentioned that Blender has a really nice Python API. The GUI is actually based on the Python API. So like if I hover over any button in the interface, you can actually see, in addition to the description and a shortcut, it shows you a Python command that corresponds to this operation. So for instance, and so if I scale, then I can sort of drag to scale the object. And you can see in here, once I complete the operation, it shows sort of the parameters that it applied, and you can actually edit it after the fact as well. So you can scale it in different dimensions, you can constrain it, you can tell it the orientation. So there's a lot of sort of options here that generally you just want to make it bigger or smaller, but it exposes a lot of parameters, and those are actually all accessible in Python as well. So you can actually, if you right-click, you can just go right to the Python reference for the resize function. And you can see they document, it's all the same parameters that you have in the GUI, but in a Python API. So this is really cool. Now you sort of have an environment where you can create and manipulate 3D objects, and you have pretty much for free with Blender a Python API to do everything that you could do in the GUI. So that's awesome. So let's go back here, and hopefully this will work. So the main Python module in Blender is bpy, and it's what I described. It's the programmatic equivalent of all the operations in the GUI. It's the way that it expresses stuff is very imperative. So it's really good for building macros. You basically say it's the same as how you would operate in a GUI. First do this, then change the selection, then do this other operation to the new selection. So it doesn't really feel like you're coding, sort of like it's hard to code Pythonically, I guess, because you're basically just listing a series of instructions. I mean, you can do more advanced stuff, but it's really hard to sort of introspect the meshes themselves or do interesting things at a lower level. You're always just sort of selecting some stuff in it to put into the context and then applying the operation. That sort of sounds a little bit abstract, and it's a little more clear if you look at the method signature. So this is what I opened up in the browser earlier. There's a lot of options that are not that important, but one notable one that's missing is there's nowhere to input the object or objects that you want to resize. That's sort of implicit in the Blender runtime. The assumption is that you would, before you call resize, you would first call get object named X, get object named cube, and then select all vertices in object named cube, and then resize. And the resize is implicitly applied to the selection. So it doesn't really feel right, at least to me. It would be great for more of a macro type thing, but not a great foundation for a larger, more complex application. I did discover there's another API in Blender called bmesh, which is a lot closer to what I wanted. It's objects for a mesh, objects for a vertex, for an edge, for a face. You can iterate through them. You can add, remove them. You can look at the coordinates of each vertex. So that was really cool. Unfortunately, it's not perfect. Since it's so low level, there's a lot of responsibility on the user to ensure the consistency of the mesh. So what is mesh consistency? Imagine I define a face that does not have edges around the side of it. That's something that just doesn't make sense. You could never actually create that in the GUI, but because of the way this data structure works, you could conceivably create that in here, and then if you try to do some operation on it, who knows what would happen. Maybe it would crash, maybe it would yield incorrect results. So you need to be a little bit careful when you're using bmeshes, because you can sort of get yourself into a bad place. It's also really tightly coupled to C, which is good, again, because you have a lot of access to the data. But if you're modifying this data, like you can, I was getting some seg faults and other things that you usually don't encounter in Python. And the other thing is that it's it's well documented, but it's sort of scary when you come upon the API. So I don't know if you can see this, but there's like 3 warnings on the module page. One of which is a warning that it's in development that's dated 3 years ago tomorrow. So I think we should, tomorrow I'm gonna have a 3rd birthday party for that warning. But contrary to the warnings, I think they're just being conservative, or maybe just no one's looked at it in a while, but it actually worked really well for what I wanted it to, despite sort of not a ton of examples that I could find online. So I'd like to maybe help that out a little bit when I get some time. So it's a little bit scary, and you need to be a little bit careful, but it does a lot of cool stuff once you figure out the sort of how it all works and how it all fits together. So as part of the bmesh API, there are operations. So these operations generally correspond to those same buttons in the GUI. They're operations for resizing and the adding vertices and edges, sort of like what we were doing in the GUI. And a lot of them are actually implemented as bmesh operations internally. They just sort of have this extra wrapper that adds the GUI stuff around it. And they're, for the most part, really well documented. There's doc strings for all of them. So I'll give the Blender team a lot of credit for, despite their warnings, doing a really good job of keeping it all up to date and completely documented. So here's the equivalent operation of what we were looking at before, but in bmesh. So this one probably looks a lot more comfortable. There's a lot fewer options, which I think is kind of weird, but basically here's an operation that you want to scale this bmesh object. And spaces, don't worry about that. Basically you're specifying so you're basically just telling it what bmesh to operate on, and the vector to scale it to. So remember how there were the X, Y, and Z factors for scaling in the GUI. This is the same as that. You just specify them as a 3-dimensional vector. So you would specify, scale 2x in a factor of 2 in x, a factor of 2 in y, and 2 in z, something like that. The last thing here is a list of vertices. So this is actually was confusing to me at first because you're already specifying the mesh that you want to operate on. But once I understood what it was actually doing, it's actually really cool. So you give it the bmesh object because that's sort of what in the GUI it's the equivalent of what object you're editing. But then the list of vertices is the equivalent of what you have selected. So you can actually scale just a couple of the vertices within an object. So that would be just like selecting a couple of them and then scaling them all up and down. So it might be hard to visualize, but it seems redundant, but it's nice that you have the flexibility of modifying just a subset of the overall mesh object. Another cool thing that Blender provides in the Python API is a module called mathutils. And this is not really Blender specific. In fact, you can it's available in pip just as a standalone module. It's just a whole bunch of classes and functions for 3D stuff. So matrices, vectors, Euler, quaternion if you're doing crazy rotation stuff. So yeah, it's just really nice, fairly simple libraries for that stuff. And of course, they're used in the bmesh module to represent the coordinates of a vertex and stuff like that. So I wound up using this a lot in even for stuff that wasn't touching Blender in what I was building. So at this point, we've sort of gone down this path of all the cool stuff in the Blender API, but I want to refocus on what were we actually doing when we started. So we're building a table. So I just wanted to refocus on that. So we sort of seen what Blender can do. We can see what we want to end up with. It still isn't super clear how to fill in that gap. So we have some 3D stuff. We have an input model, but we don't necessarily have like that last little bit of glue. So that's the other part of what my talk is about, which is a module that I wrote called Sly. And the way I describe it is a Python library for 3D construction from 2D parts. So it's a Python library to do what I need it to do. Right now it uses Blender to input models and to render output, but it doesn't really use that much internally. It uses that mathutils library like I talked about, but the underlying data structure, it doesn't really make too many assumptions that you're actually running it from inside Blender, which I'll get to later. It's also really small. Last night I did a line count on it, and there's only about 350 source lines of code in it, which made me feel kind of dumb for it taking like 3 months to write. But I think that's sort of in the Python spirit of, it took me that long to just strip it away to only 350 lines. So the two core concepts in Sly, they're basically just the two objects. One is a slice. So a slice is a 2D polygon that has thickness positioned in 3D space. So if we go back to this image here, you can see one of these, any one of these individual parts is a slice. And when I say they're positioned in 3D space, they have an orientation. So they might be, facing you, the audience, or they might be parallel, going the other way. So that's the orientation, and then they also have a position, so where they actually are. So that's, but fundamentally they're a 2D object. So that was sort of the core data structure that I was missing, that I felt like I could sort of build some stuff around. And then the other thing is that slices have cuts. So a cut is what needs to be removed from a slice so that it can interlock with another slice. So probably maybe get it at this point, but a slice is these little cutouts, the cuts. Hopefully it's self-explanatory. So with just those two concepts, I was able to it was basically just a lot of translation. So the first translation, okay, I guess we're doing this. Let's try, there we go. Now the fun part of trying to hold the mic while doing a demo. So I'm going to open a different file. So this has the shell of the model that I built my table out of. So you can see going into edit mode, it has a whole bunch of vertices, and the same sort of thing, but there are additional modifiers on it, so I actually didn't have to do the whole thing. I could sort of mirror it and make it symmetrical and then smooth it out. So, but this is still, even though it's smooth, it's still a mesh. It's just a more complicated mesh than the one that I have to edit. So we have this object, which is a mesh, and then we have this script. And this is not Sly. This is the macro, or whatever you want to think of it. This is what implements the functions in Sly to do something cool. So I'm just going to sort of go through it. Yeah, so again, just a list of the slices that we want Sly to extract from this model. So the z-index, don't worry about. That's just sort of how it has to do with which way the cuts come out, whether they cut from the top or the bottom. So this is it. This is all the code that interfaces with Sly to create the model. So the first line 48. Hopefully you guys can read this. If not, it's on GitHub. So there'll be a link. So line 48 here. We're just asking for whatever the selected mesh is in the context. So I basically put all of the wrappers in this bcontext module. And then this is sort of the magic method, the two slices. It takes that mesh, it takes our list of slices and the thickness, and it outputs slice objects. So this is sort of where all the magic happens, where it'll actually do all of the, create the cuts and do all of that other cool stuff and just output these slice objects. And then we can do stuff to those slice objects. So here, I'm applying an operation. So this is in the Sly library. There's a border operation. So this is exactly what I wanted to do that I couldn't in 123D Make, which is that I wanted to sort of just cut out the centers of each piece and just leave a border of a certain width so that it looks more skeleton-like. So I just implemented that. Then added so then I create a page. So a page is just sort of a 2D, a holder for the 2D representation. And it doesn't really do much now. It's at some point in the future, I'd like it to like automatically position them so that you can just feed that right into the plotter. But right now, it just sort of lays them on top of each other, and then it just adds them back to the to Blender as well. So, and then it writes the writes an SVG file out. So when I run this, it's going to add the slices to Blender, and then also going to output an SVG file. So run script. We have the object selected. It takes a couple seconds, and now you can see if I hide the base object, it's created those slices. So these are all individual objects right now. So if I can like move them up and see the cuts in them, which is kind of cool. And so this is so these holes here are what was created by that border operation that I mentioned over here. Sorry? Yeah, no sanding in the rendered version. In real life, it's not quite so ideal, but so in addition, so I mentioned it also outputs an SVG. I'm just going to show the screenshot of it because I don't want to open Illustrator. So this is in case it didn't work. So this is not what it outputs. This is me manually positioning the objects. So I'd like to get it to a point where it does automatically position this, but it doesn't do that yet. So I have to manually rotate them and put them in a place so they don't overlap, and so that I can actually cut it out. So another interesting thing here to note is that the cuts, which are in blue, are separate vector objects from the pieces themselves, from the slices themselves, and that's deliberate, really for machining reasons, because sometimes you might want to use a smaller or finer bit to cut the cutouts, and then use a larger bit that can go faster around the whole thing. It also gives you a little bit of flexibility. You can actually change the offsets of those cuts, the thickness of them. So if you didn't get the measurement of the thickness of the material exactly correctly, you might be able to sort of fudge it later on in the processing pipeline and not have to re-render this whole file. So I found it was kind of nice to keep them as a separate layer. So this is another cool thing about using Blender is that you get really nice renderings of what you're going to build for free. So this is not something that other CAD applications can necessarily do. So when I sort of realized that, I had to spend 10 minutes and get the lighting right and make a cool rendering. So here you can actually see it's an earlier iteration that had little wooden fingers that came up around the sides to hold the tabletop, and I decided I didn't really like how that looked. I'd rather have it extend all the way further. So I'm going to just talk a little bit about what's inside of Sly, and then I'll wrap up. So this is sort of the killer Blender method that I use to extract the slices from a model. It's called Bisector Plane. And it takes a mesh and a definition of a plane, which is what I described before, where it's a point that lies on the plane and sort of what way the plane is facing. And it'll create edges all around the object at that point. Actually, let me see if I can illustrate it. It might be easier. So I'm going to, if I can find my tools. This is a different, here we go. So if I do bisect and I draw, you can see it's sort of drawing a plane through this object. And then if I release, it actually creates edges around that plane. And then it also has this extra effect where it can clear the inner and outer. So basically, imagine doing this where I define the planes, and this is the polygon that I use to create the slice. So I luckily didn't have to figure out how to do that part. So that's sort of one cool part of what's inside. Another cool part is Shapely. So again, I didn't write the Polygon stuff. I used an awesome library called Shapely. It's mainly for GIS, so like doing stuff with mapping data. But it's really good for just sort of general purpose. What's the intersection of these polygons? What's the what's the difference between them? It's pretty high performance, which I didn't really care about at this point, but people say it's good at that. So all of the polygons are Shapely internally, which is another cool library if you want to do stuff with shapes in Python. So that's sort of where it's at so far. This is some of the ideas of what I want to do with it next. I just open sourced it last night, so it doesn't have an installer or tests or docs or anything like that. I'm sort of hoping this talk will be the doc for at least for a little bit. Command line operation, so instead of just using Blender, be able to give it a model and generate the stuff on the command line, because I think you could do some cool stuff if you could automate it. Better, and then sort of in contrast to that, better GUI integration, so being able to maybe have it automatically be re-rendering as you make changes to the model instead of having to run it separately, or sort of do other, sort of have it exposed as one of those buttons in the toolbar instead of just a little script off to the side, which is doable. It's just sort of a matter of wiring it all in. So slice placement, which I mentioned earlier, when it's positioning in 2D on the material for you to cut out. One thing I was thinking about is outputting directly to G-code. So instead of having to create a vector file and then take that and just go to this other program to generate the toolpaths, actually just generate the G-code directly. There's some challenges in that, but I think it might be interesting, which also depends on placing the slices. And then different construction modes. So I don't really know what that means, but something other than just fitting slots of wood together might be cool, but I don't really know what that could be. So that's sort of the idea. So if this is interesting to you and you want to help or learn more, I'm going to be doing more in-depth sessions on sort of the whole process, so not just the software side, at Pumping Station 1 in April. I haven't locked down a time yet, but if you're interested, email me or contact me somehow, and I will let you know when I've figured that out. Also, like I said, it's on GitHub, so you can poke around the code and contribute maybe, or at least tell me that it's broken, because I've only run this locally and might have forgotten some dependencies or something. So that's it.
Take some questions and then hand them. All right, we're going to take some quick questions, and then we have a couple of small announcements after the questions, and then we are free to socialize and stuff.
So I noticed one of the early lines in your script is that you had you kind of defined which axes you're slicing on. Have you tried doing a non-90 degree kind of or a radial type setup? That seems like that'd be pretty cool.
Yeah, it's a really good question. So the question, in case you didn't hear, was about non-perpendicular, non-90 degree slice intersections. That would be really cool. One problem is that you need to be very careful about how wide you make the slice, because there's some trigonometry to do that, and then they're not going to be as rigid. So I was thinking of some ideas that sort of use triangles that fit together, which would be at least as strong. So yeah, that's a cool idea. I'd like to do that.
One constraint is that the shop bot will only cut on 3 axes. So that would be a problem if you were trying to cut something that would be that the CNC machine would not support cutting off of an axis. But he had a question.
Oh, the G code. Were those coordinates? Those are 3D coordinates, just regular straight 3D coordinates? Okay, and you didn't bypass them on the second time around once you started using slot? You still had to use them? You still had to use the vector V, whatever it was?
Yeah, so the question was just about whether the G code is still necessary was vcarve still necessary? So the part that converts the vectors to G code. So yes, because the output of Sly is vector, it's not G code. So I still need vcarve to turn the vector file that's my output into something that the shopbot can use. So that step is still necessary for now. That would be the benefit of being able to generate G code directly.
In 2D, is there a value of the thickness of the board that you need to specify when it converts to 3D?
So I think if you're asking just whether the thickness value is used in 2D, so the reason that thickness is sort of a fundamental parameter is that you need to know the thickness to create the cuts. So the thickness, because of how they intersect, corresponds to the width of a cut. So if you were using wider material, then you would need to make wider cuts for that material to fit in. Other than that, it's not used in the 2D output. All right. Cool. Yep.
When you're calculating the vectors for the cut, do you take the width of the router into? You can.
Yeah, so the router bit has a thickness of itself, so you need to, when you're doing sort of precision stuff like this, you would need to take that into account. Fortunately, vcarve, which is what takes the vectors and turns them into the actual G code, you can tell it whether you want it to cut inside or outside the shape. So actually what I showed you before, I would tell it to cut outside the main shape and then inside the cut, and it would just do it because it knows the thickness of the bit. So that's it.
Great, thank you very much. Thank you. Real quick, couple of things. Thank you, Matt, that was great. Before you jump out to IKEA, go to Pumping Station 1.